Okay, so today we're going to continue um, learning not just what differentiation is, but how to do differentiation, how to use differentiation to solve maximization problems. Because in economics, a lot of the problems you're trying to solve boil down to some kind of maximization or minimization. Have you ever thought about this? A maximization and a minimization is really the same thing. Anytime you're trying to maximize a function or minimize a function, it's exactly the same procedure if you just have a negative sign out front. To minimize f of x is the same as maximizing a negative f of x. So as long as you're comfortable with multiplying things by -1, then these are really two of the same things. However, we should care about how something is written as a maximization or a minimization problem because we want to be precise about the way we solve such a problem. We want to make sure the solution to a problem is correct. And therefore, what I'm going to do is eventually, I think today we'll have time to talk about these conditions for what a solution should even look like. I think most of you already know we're talking about with just functions of one variable. You can almost picture in your head what that would look like. And if you can't, I'll review that with you today. But the goal is to get a good foundation of how the optimization procedure works with just one variable so that in the future, we can do this with multiple variables. That's the goal, right? By the end of this class, I would expect you to be able to solve a maximization problem with multiple choice variables. In other words, you talk about a person who can choose X, can choose Y, can choose Z. And the thing that they're trying to maximize is some function of X and Y and Z. That's already impossible to visualize because if a function has 3 input variables, the function itself is an output variable. That's 4 dimensions. And nobody in this classroom or anywhere really can visualize 4-dimensional space because we live in a 3D world. Our brains exist in a 3D world. We can't visualize 4 dimensions. So you can't rely on your visual intuition to solve those problems, right? You actually need a mathematical, not algorithm, but system. Relying on math is better than relying on what it should look like in your head. Relying on what it should look like is a nice shortcut for simpler problems, but it gets you almost nowhere in the more complicated problems. Okay, but first we should do the simpler problem. And let me share my slides on differentiation because we haven't quite finished that yet. Oops. I thought I shared it. No. Share screen. Differentiation. 3. Share. Yeah. Enable editing. Slideshow. Okay, before we do that, we actually looked at a few of these, and I don't want to do any more of these, but how about some of these? This is also perhaps some practice with treating variables, treating some variables as constants rather than or here we have this other equation, v equals 1/3 t cubed. These are a little bit more complex versions of differentiation, but I kind of think they're all telling you something about the flexibility that you should approach these problems with. Don't look at them in a sort of rigid, fixed way where I have to it has to look like f of x equals something with only x's in it, then I can do it. But once you throw me something with some constants like a, p, b, q, or it's a v here, and I'm supposed to be taking the derivative with respect to t. If you really think about the process of differentiation correctly, I don't think any of this will throw you off. Because in each of these problems, you're really just thinking, how does this one variable, y, in two-way, how does y change with respect to t? That's what I'm looking at. And the tools, who cares if there's a v in there? Well, v is a function of t. We can use that to get ultimately what we want, which is dy dt. So somebody want to say, how would I do this first one, 2a? Let me write it here. Y equals -3 v plus 1 to the 5th. And by the way, v equals 1/3 t cubed. What should I do here if I want to take dy dt of that?
Couldn't you plug in v though?
You could plug in v. Yeah. Is that how you would do it? You know what? It's not wrong. And then you'd have a function only of t and take the derivative of that. That would be fine. If you didn't want to do that, you could just take the derivative first with respect to v and then multiply it by the derivative of v with respect to t. That's using the chain rule a little bit more explicitly. What you're talking about is just eliminating v and then taking the derivative. That's okay too. What would you get? Who is that talking, Brian? Was Brian talking or somebody else?
No, it was Jonathan.
Jonathan. Okay, yeah. So
I originally did it the chain rule way, which is -15 v plus 1 to the 4th times t squared, and I just left it like that.
Yeah, that's fine. You guys see how we got that? Let me. If I have to, do I actually have to stop sharing in order to pinpoint this highlight spotlight for everyone, right? That's how we could do this. We could just leave it as v, take the derivative of it. This 5 times the 3 becomes -15 v plus 1, the same base, but the exponent is reduced by 1. It's v, 5 minus 1 is 4. And then we multiply it by, because of the chain rule, dv dt. So this right here is the derivative of v with respect to t. 3 times 1/3 is 1. That becomes t squared. Everyone see how that's equal to dy dt? That's correct. How about some of the other ones? Why does it keep going to that? Practice with second derivatives. Why does it keep going here? I'm not sure. Are you seeing the spotlight or are you seeing move spotlight? Okay, let's pick some of these other ones to do. They're all maybe a little bit different, which is why I selected them. I'm going to write them all down. X to the a times px plus q to the b power. That's one of them. Another one is c equals 20q minus 4q times 25 minus 1/2 x squared, or x to the 1/2 power. And then the next one is find the derivative of f of x quantity squared over x cubed. And the way I would write that is just to let you guys know. Okay, so I'm going to switch now to my phone and the writing I've been doing, and I want to highlight. Is this pinpoint? Is this spotlighted? Spotlight for everyone. Okay, I think it's spotlighted. So for that last one, how would I write that? I think this is a nice way to write something like that, where it's not just dy dx, it's not d of f of x dx, it's the derivative with respect to x of something that's a little bit more complex, something like this that has a function in it. That's okay. I mean, what if the function was y equals f of x? That wouldn't make you think it's too weird. And so you might ask, well, why don't I put just the y there instead of f of x? Well, I would put something like f of x if I wanted to highlight the fact that this is still a function of x. It's not a constant. This thing, whatever I have here, f of x, is some function of x. I can still take the derivative with respect to x of that whole thing. But let's do that last. That's maybe the hardest one. So we did the first one. Here's the second one from my slides. How would I take dy dx here? You may want to tell me what to do real quick. You see? What do I do? What's a rule I use?
The product rule.
Product rule, that's good. It's going to be ax a minus 1 times, now I just leave this part the same. Then I add that to leave the first part the same and take the derivative of the second. I would say b px plus q to the b minus 1. Don't forget the chain rule times p. I think that's the answer, isn't it? See how I use the product rule here? U prime v plus u v prime. You can think of it that way. Is there any questions about that? Does anybody look at this and still feel like, uh-oh, there's a bunch of letters there, like A's and B's and P's and Q's? I'll tell you, that happens all the time in economics. When you're measuring demand or supply or profit functions or something, a lot of times it involves parameters, and the parameters will take the form of A, B, something like that. And you still do calculations, evaluate things, leaving those parameters as letters. It shouldn't change the way you do your calculus, your differentiation. So no questions about that one? That was the second one from that slide. So the third one on the slide was this one. And I wanted dc dx, I believe, right? Let me just check. The slide asked me to find dc dx, yeah. Which is kind of good news because I can treat this q as a constant. I can treat that q as a constant. So actually that first term just goes away. I don't even need to worry about it. Doesn't it? Okay, and then what about the second term? I treat that negative 4q as a coefficient, as a constant. I'm going to leave it there. You can always take the coefficients outside of a derivative, meaning you multiply it. Sorry, go ahead.
Why wouldn't it just be 20?
Oh, because we're doing dc dx.
Oh, okay. So it's just.
So 20q is a constant.
Yeah.
What's the derivative of a constant? It's 0.
Yeah.
Yeah. So if you're right though, if it were dc dq, then you would leave, then it would be 20. There would be a 20 there. Don't you agree?
Yeah.
Right. So it really matters what you're taking the derivative with respect to.
Okay.
Yeah. So also I have to mention, what if q were a function of x? If q were a function of x, then I can't ignore it. I can't just say, well, the derivative of 20q equals 0. And we'll talk about this later. What you would have to do something there is called a total derivative. Right now, we're just taking the derivative of one function c with respect to x. And we're treating q as if it's just totally a constant. However, in just a couple weeks, we'll start talking about the case where actually q might be a function of x, and I want to take the derivative of c with respect to x. I still have to think about the way that x affects q. And I'm sure you know, you already have some idea of how that would work, but we'll formalize that later. Give me like 2 weeks and we'll get to that. Okay, but for right now, Q is a constant and it just disappears.
Okay, thank you. I got
Now
it.
we go to this constant I just kept there. I'm still using the power rule. This 1/2 becomes a multiplier here. The 25 minus 1/2 x remains. But now instead of to the 1/2 power, I'm going to reduce the exponent by 1. It will become negative 1/2. There's a negative there in case you can't see it. And I'm still not done because of the chain rule. I have to multiply it by the derivative of the inside with respect to x, which is negative 1/2. So that would be the answer. Whatever that is, you simplify it if you want. But I already see a -4, a 1/2, and a negative 1/2. Those would all cancel out. And you would just have a cube on the outside. I'm not big on that. I'm not going to force you to simplify. If I do want you to simplify, I'll ask you to. But in general, I noticed on the homework, a lot of people did, and that was nice. But even if you didn't, I still gave you full credit. Oh, by the way, on the quiz, on the national income model of the quiz, I asked you to solve the model. You really should have given me the answer for Y and C, because they're both endogenous variables. You should have solved it for Y and solved it for C. But in this particular case, I think it was just so easy to tell what C was. Like if you solve for Y, it's obvious what C is. And the fact that you didn't write it down isn't some, you know, grave error in your mathematics. It was just didn't quite understand what I was asking for. So I decided to give you full credit this time. But in general, if someone's asking you to solve a model, they want you to find all of the endogenous variables, not just the maybe the most important one. You were right that Y is the most important one, but just something to remember in the future. I gave you a pass this time because it's quiz 1. Okay. I'm going to do the last one now. This one might be the hardest. You guys know how to do this one? What do I do for this? Any ideas?
The quotient rule?
Quotient rule. I like that idea. Okay, so it's going to be the quotient rule with let's call it the top u. U equals f of x, the whole quantity squared, and v equals x cubed, right? And I was just did it last night. So the answer to the quotient rule is u prime v minus u v prime whole thing over v squared. All right. So this is you don't have to write this. What I've put here in this little box is just like a way to keep track, like a record keeping system that helps you not make a mistake. That's what I'm doing. That's why I did it. But I think it was Kai who said use the quotient rule. I think she's absolutely right. That's the best thing to do here. Okay, let's answer it. What would let's do the top. The first thing is u prime. What should I put here for u prime?
Is it just 2 f of x?
What do you guys think? Is she right? You're very close to being right, but not quite. Something I have to add to this, or actually multiply.
You have to multiply by f prime.
Yeah, you do. You have to multiply by f prime. You guys see why I have to multiply it by f prime? I mean, it's the chain rule for one thing, but I'm taking the derivative with respect to x. So of course, there's going to be some part of this that involves f prime of x. It's because I'm taking the derivative, right? The derivative of u, whatever some function squared, it's going to be 2 times whatever that function is, times the derivative of that function. That's basically just the chain rule at work. And I don't want you to be like freaking out because it's not a variable there. Just because it's written as f of x, that's okay. You can write things that way. And so this is the proper thing for u prime. Then for v prime, I'll just write times x cubed. Not prime, I'm sorry, just v. Minus u, I'll just write f of x quantity squared. And for v prime, I think you know that's 3x squared. And then x cubed, oops, sorry, v squared is x cubed squared, which is not x to the 5th, it's x to the 6th. Okay, that's the answer. And remember, I got this problem from the Sid Sayer textbook. You can always go back in that chapter and see problems. You can see this problem and a bunch of problems just like it. Gallery view. Yeah. It's section 6.8 of that textbook. I want to get on to some later things. I also want to talk about second derivatives. How do you guys feel? I noticed some people missed the problem about 2 to the x and 4 to the x, and how do you deal with these logs and exponential functions. I think it's worth having a little more review on these. Oops, this one. And look what I'm telling you to do right now. Simplify the following before differentiating. Don't try to differentiate it and then simplify it. What's this first one? I think we can do this in our head. What is the natural log of e to the x divided by e to the 1 minus x? That's before we do anything, just simplify that. What would it be? Any ideas? How about let's do the fraction first. First, simplify this fraction. What would you get? What is e to the x divided by e to the 1 minus x? Nobody knows? This is a problem. Do you guys, are you guys confused, or are you just bored about how to simplify exponential functions like this? I'm talking about what is e to the x divided by e to the 1 minus x. Forget about the natural log right now, but just combine those into one exponential function. What would it be?
e2x plus, or sorry, minus 1.
Perfect. He took, who is that talking? Amina, thanks. Yeah. Amina took the numerator exponent, which is x, and subtracted the denominator's exponent, which is 1 minus x.
Yeah.
X minus 1 minus x. There's 2 negatives on that x, so it becomes 2x minus 1. That's the right answer. E to the 2x minus 1. Now, if I want to take the natural log of e to the 2x minus 1, what does that become?
It would cancel out the e and just be 2x minus 1.
Exactly. It would just be 2x minus. This simplifies the 2x minus 1. If I wanted to differentiate it, the answer would just be 2. Right. And kind of a similar thing is happening here. E to the natural log of 3x, that just simplifies to 3x, doesn't it? This one, can you simplify e to the x squared? This is sort of a test to make sure you don't do something you can't do. Part of algebra and math is knowing what you can do and what you can't do. Sometimes you shouldn't simplify things if it makes it incorrect. So e to the x squared, there's actually no way to simplify that. Okay, you can't make it like, oh, e times x, e to the 2x or something. No, it doesn't work. How about this last one? You know how I always think of natural logs when there's a natural log of a bunch of stuff either being multiplied or divided. I want to separate that out. It's just so natural to think of these as being separate things rather than all together. And what I mean by that is somebody is joining rather late. It'll be my next class. Okay, so what do I mean by separate this out? Instead of saying the natural log of this entire fraction, you could say this is equal to the natural log of x squared plus the natural log of 1 minus x squared plus the natural log of x plus 3 minus the natural log of x to the fourth. Separating them out in that way will make it a lot easier to differentiate. Okay. In fact, I can tell you exactly what it'd be. The first one would become, become 2x over x squared, which is really just 2 over x. The second one would become 2x over 1 minus x squared, so plus 2x over 1 minus x squared, plus 1 over x plus 3. And then here you have minus 4x cubed over x to the fourth, which is also just minus 4 over x. But that would be the answer to that second one. The key point here is that sometimes exponents and natural logs can be simplified a lot. Before you do anything else to them, it might make sense to use that fact. I think that's all I want to say. Have any questions about that? Good to go. Higher order derivatives, of course, they're important. The second derivative, sometimes it's written like this, f prime prime of x. It's equal to the derivative of x, if it exists. It doesn't always exist, but if it does, we can use this notation f prime prime of x to denote that. There's other ways it could be written. Sometimes instead of dy over dx, it's d squared y over dx squared. I'm not even sure exactly why they put the squares where they do. I think it has to do with, in the numerator, you're just adding d's like this. You have a d here and a d here. And in the denominator, you have a dx and a dx. But really, it's just notation. Don't worry so much about it. I will probably use f the double prime whenever it's a function of one variable. I will tell you in the future, we'll have functions of more than one variable, and that really changes the way we think of higher order derivatives, because it matters, am I taking the derivative with respect to this variable and then a different variable, or the same variable twice? All of that makes it more complicated, and I will need to use better notation then, but for right now, I will mostly use f prime prime, okay? So I need to talk about what does it mean. How can we interpret f double prime? If it's positive, what will I say? If f double prime is positive, that's equivalent to f being a concave or concave up. I think this is wrong. What am I doing? Sorry. I actually think I have a typo here, and I really should fix it. And I'll have to fix it also on the slides. I just want these to be the other way around. This was a test to see if you caught it before I did. Nobody caught it before I did. Okay, I'm sorry, I'm switching these. F prime being positive is equivalent to f being what I will call convex. Another way to think of convex is a concave up function. It's bending, it's curving in a way that the derivative is increasing. The slope of the function is increasing. You can think of a bowl. If you think of a function that looks like a bowl, where you could, pour milk into it and the milk would stay inside the bowl, that's a good way to think of a convex or concave up function, f double prime positive. I actually prefer the word convex. Despite me having a typo in the slides and putting the wrong thing, the way I would most like us all to refer to this type of function is actually a convex function. That's when f double prime is positive. By the way, a function could be convex at a point, meaning the f double prime is positive just at that point, or it could be f double prime is positive everywhere. And if that's true, we call it a convex function everywhere. So it can be convex at a point, or the entire function can be convex. And those mean two different things. They're similar, but not exactly the same. Okay, now how about the other one? F double prime being negative is equivalent to f being concave or concave down. This happens when the slope is decreasing. Not that the slope is negative, but that the slope is getting more and more negative. The slope is going down. And you can think of this as a hill, a function that looks like a hill. It has a point at the top of the hill. That would be a concave or concave down function. And why do we care about second derivatives? They have important applications for optimization problems. Remember, to optimize something in this class means you're either maximizing or minimizing something. And of course, if a function looks like a hill, then there's one point there right at the top of the hill that's a very important point. That's at least a local maximum of that function. The special point at the top of the hill where f double prime is negative seems like a maximum point. Whereas the point at the bottom of a bowl, you imagine a bowl looking function, there's one point right at the bottom, that seems like the minimum of a function. So as a preview, it's a little bit backwards what you might think. When the second derivative is positive, we're looking at minimums. And when the second derivative is negative, we're looking at maximums. You may think of maximum as a positive and minimum as a negative, but it's actually the reverse. The maximum occurs when the second derivative is negative, and the minimum occurs when the second derivative is positive. What about third derivatives and higher? Of course, you could talk about a third derivative, but they don't matter much in economics. And that's what this class is about, so I'm not going to tell you too much about them. Here's some practices with second derivatives. Finally, let's find the second derivative of each of the following. You guys want to go ahead and do this, and then I'll tell you if you're right or not. I'll do it myself as well. And we'll see who gets it right, you or me. I'll tell you, when I'm writing this, I'll also write the f prime and then f double prime. If you can take the derivative, then I think you can take the derivative twice. So this isn't, conceptually, this is not any more difficult. Is anybody done? Because I'm not. It means you're faster than me if you're done. Congratulations. We might even be able to say something about whether these functions are concave or convex. Maybe everywhere they're concave, everywhere convex, or just convex at a certain point or concave at a certain point. We'll talk about that in just a second, if you don't mind. Are you working on these derivatives?
Yes.
Thank you. Are you done? Anyone done? Ooh, do I have to use the quotient rule for the last one? Boo for the quotient rule. I say boo because I often just forget it and I need to remind myself what it is often. Minus u e prime whole thing over e squared. Okay, I got it now. Time to reveal the answers. My phone. Spotlight for everyone. Can I go ahead? So I got for the first one. It's pretty simple. You just do the power of multiple times. Okay, let me ask about whether it's concave. Let's take the point x equals 1. Would you say it's concave or convex at the point x equals 1?
Convex.
Correct, because it's positive. F double prime is positive. Oops, that's supposed to be double prime. Positive, then it's convex. Good one. Okay, how about this second one? Is this what you got? This little 2x thing kind of disappeared over time. When you're talking about the F double prime, all I got was 4e to the 2x. So it's kind of interesting how every time you do it, another 2 comes out here. So, once again here at the point, let's say x equals 0 even, it's convex. It's pretty much everywhere convex, isn't it? E to the 2x is always positive. That's an always positive function. So F double prime is everywhere convex. I'm sorry, F is everywhere convex because F double prime is always positive, which is kind of neat. Here we had this one point where x equals 0, where it's not positive, but pretty much everywhere else we can be sure that F is convex. So 2 very convex functions we have. How about the last one? This was the one where I had to use some quotient rule. I did it right. Tell me if you guys got the same thing as me. First time I did 1 over x squared plus 1 times the derivative of x squared plus 1 is 2x. Got that. That's the first derivative. Second derivative, I had to use the quotient rule. 2x squared plus 1 minus 2x times 2x. That's the last thing here, supposed to be an x. Over x squared plus 1 squared. Yeah, is this ever concave? What do you think? I think it might be. Yeah. Sure it is. What do you guys think? I'm gonna pick a point like x equals 2. At the point x equals 2, is this F convex or concave? One hint is that you can pretty much ignore the denominator. That denominator is always positive, so forget about that. Well, let's plug x equals 2 over here. We have 2 times 2 squared plus 1 is 5, so that's 10 minus 2 times x times 2 times x, that's 4 times 4 is 16 over, all right, I'll do the denominator. 5 squared is 25. But this is negative, so actually this f is concave at the point x equals 2. I actually think this f switches from being concave and convex, doesn't it? There's some values where it's concave and some values where it's convex, so that's kind of interesting. But yeah, for example, at x equals 0, it has to be, for x equals 0, it has to be convex because this part goes away, this part's positive over positive. So f double prime would be positive at x equals 0. So we'll see why this matters in a bit later. With that, a function being concave or convex, it really says something about what type of optimization is possible for this function. Could this be a maximum? Could this be a minimum? You'll see that in a bit. You guys have any questions about that? I think we're ready to talk about optimization with one choice variable. This doesn't look quite right. Okay, so chapter 8 of Sid Seder, the textbook, the Sid Seder textbook. Am I still spotlighting? I'm not, right? How about that? Is that better? I just want you to be able to see my PowerPoint slides right now. Let's talk about this, how to optimize. Okay, fine, I want to know why would you optimize? It's to solve some economic question, like what price should a firm sell its product, or even how much fertilizer should a farmer use to maximize profits? How fast should an oil company extract oil from a well? If you get it too fast, it might dry up. If you get it too slow, you might not make enough money. How big of an oven does a pizza shop need to buy? Okay, these are all just questions where if you made it in the form of a model with a function and an objective function. Notice in all of these, there's some sort of objective function. That's my third dot. So I'll get to that in just a second. When someone wants to model one of these questions, like these first 4 questions, the thing you have to do is describe the relationship between whatever the variables of interest are, the things that I'm actually interested in. Let's talk about those and how they're related to each other using math. An important thing is to determine the choice variables and choice set. Do you know what I mean by that? You comfortable with this term, choice variables or choice set? It means, it's kind of obvious. Choice variable is the variable that somebody is choosing. They can get to pick something. That's called a choice variable. And the choice set is just the set of all possible choices. So it's just going to, like, plain English, I think it makes sense. But it's important for this whole modeling procedure. You want to model an economic problem as an optimization problem, make sure you talk about what the choice variable is and what the choice set is. Without that, it's sort of incomplete. It's not a complete problem. And then also, of course, you determine the objective function. That's the thing the person who's making the decision cares about. So, you know, in the first dot, I would say the person cares about profit. Second one, profit. Maybe on all of the ones I gave you, it's profit, but you still have to find some way to calculate the profit as the thing that the person wants to maximize. And that's called the objective function. It's possible you want to minimize an objective function too. So just because something is an objective function, that doesn't mean, oh, we have to maximize it. No, it means either max or minimize it. The best example is cost. You would want to minimize your cost of doing something. Or, you know, pollution, you'd minimize the pollution that you would cause, or you would minimize anything else that's considered bad. You want to minimize it. Okay, let's talk about a little more about these problems. I want you to be familiar with this terminology and this notation. I should maybe even call it both. I'm giving you both the terminology and the notation that I like to use in this class. Here's how you will see in its most general form a maximization problem. Just the word max, f of x, is the function, that's the objective function that you want to maximize. X here is the choice variable. And I know it's the choice variable because it's written almost as a subscript directly underneath the word max. That's what that means. When you see the word max and then directly underneath it, there's a variable such as an x. That means the x is the choice variable. But you should also see very near the x, this curly thing that looks like an E. That's really, it's like a set theory symbol that means is an element of. That's what that means. X is an element of the set. Here I have, for example, capital R, which in general is just some choice set. Maybe in this R refers to real numbers, but I'll be clear about what the choice set is. This is the simple case where X could be any real number. You might write X is an element of R. So this tiny little expression here, max X in R, sometimes you read this symbol as just the word in. Just for as an abbreviation, you say max of X in R of f of X, right? That's the whole problem right there. That's what I would like you to be able to do. Okay, now let's talk about the terms of that might come up. If there is some value, let's just call it C, such that the objective function f, when evaluated at C, or that's just f of C, is greater than or equal to f of X for all X in the choice set R. If that's true, then we call C a global maximum. Why do I have the word global in parentheses? Because sometimes if it's not there, if you don't see global maximum, you just see a maximum, it's referring to global maximum. The default is global, okay? The default is, oh, C is a maximum. That means, oh, C is something which maximizes the function f on the range R, or the choice set R, okay? So what about if it's not a global max? Then the other thing would be called a local maximum. And what does that mean? It's actually not what you think. Like local isn't like a little district or a precinct. It really just has to be in some neighborhood of C, meaning the values of X that are very close to C, one direction or another. It can be a really, really tiny neighborhood of C. It doesn't have to be a big neighborhood. And it's not like, the United States and then there's one state, which is still a pretty big part of the world, an entire state like Virginia has to be a maximum for that whole state of Virginia. That's not true. It could be a maximum just for a really, really tiny neighborhood. And it's still called a local maximum, but that's the terminology we'll use. And similarly, if f of C is always less than or equal to f of X, it's a global min. And if it's a neighborhood, you would say local min. This term extremum is the generic term for either a max or a min. It's pluralized extrema, but extremum just means either a max or a min. Like I haven't determined yet whether it's a maximum or a minimum. It's just one of the two, call it an extremum. And then the word unique or strict refers to the fact if there's only one maximum. Given this problem, right? X could be anything in R. R is some range, we'll say. X could be anything in this range R. And if there's only one global maximum in R, then we call that the unique global maximum. You might say if it's a global max, doesn't that happen to be another one that is also a maximum? Well, they could be tied. Yeah, right. So it does mean something to be unique global maximum. Okay with this terminology? Go on, let's go on. Oh, more terminology, oh boy. If C is a solution to this problem, where now X isn't just, let's say, the entire real numbers, but some interval between A and B. I hope you guys know that there's this, there actually could be a difference between a closed interval and open interval. The difference is, if you use parentheses, that means it's the interval between A and B, but not including A and B. That's what the curved parentheses means. Whereas if you see the brackets, it means it's the interval between A and B, and it includes A and B. So there's an important difference there that I'm basically talking to you right now about. That says, if I give you this problem, maximize f on the range X in the interval A to B. If you find a solution, let's call it C. If C is some solution, and it happens to be in the interval A and B, but not one of the two extremes, you call that an interior solution. So I want you to know what it means when we say interior solution. It just means it's not one of the two boundaries. And if it is one of the two boundaries, we call it a corner solution. So if the maximum of this problem happens to be when X equals A or when X equals B, you call that a corner solution. It's sort of, you might say, what's the corner? It's just a line, there's no corner. It'll actually make more sense when you start talking in multiple variables, maybe, this term corner solution. Although it makes sense now. It's the corner of the interval, I guess. Where are we? I don't even know which time we have. I wish my phone would tell me, but it's zooming right now. What the book often calls any point for which f prime of C equals 0 is a stationary point. It's stationary in the sense where, if you think of f as a function that's moving up and down, well, if you get f prime equal to 0, that means it's not moving up or down. That's how you can think of it as stationary, like fixed. Even though it's not fixed, because if C were just to go a little bit further, then maybe the derivative would change and it would no longer be fixed. But it's more like at this instant, f is stationary. So you call it a stationary point or a critical point. Either one of those those are synonyms. You say f is differentiable if its derivative exists at every point in the domain D. Functionally, or effectively, what that means is you can't have a gap in the function. If the function has a gap in it, it's not differentiable at that point. Or if it has some kind of kink, let me just stop sharing and look at you guys for a second. You guys know, oh, not full screen, gallery view. You guys know what I mean by this, by a kink. If a function's going up and then it really quickly goes down like that, that point where it switches really quickly, the slope is non-differentiable. And that can actually mess up your optimization problems, unfortunately. If you're an economist and you're working away, and you're like, okay, I have the solution, here it is. You may be wrong if there was some non-differentiable aspect of the function that you were maximizing. You might say, oh, well, I have the solution, it's right here. No, not if there's either like a discontinuity where there's a jump or a gap or a kink, something like that. It's rare, but it can happen. So let's, for the time being, focus on differentiable functions which don't have these issues, continuity or, kink, and we'll be able to use these procedures a little bit better. What's happening? I guess every time, here we go. So I would also like to say something about logical statements because I would like to use them in this class. And what do they mean? Sometimes I will use an arrow. I don't really think I'll use an arrow very much. It's really these two at the bottom that I'm going to be using. And the book uses, and economists often use. And just so you're not confused, I really want you to know what they mean. What does it mean to be sufficient for something? What does it mean to be necessary for something? They're almost opposite directions in this arrow, in this logical statements. I've written 6 dots here, 6 sub bullet points. Each of those statements are logically equivalent. Okay, and even include the 7th if you include this arrow. P implies Q. In fact, that's how I would read this. When I see an arrow, I read that as implies. P implies Q. That's equivalent to Q is implied by P, of course. There's just a way to rephrase the sentence. You can also say if P, then Q, right? If P happens, then we know Q must happen. Whatever P and Q are. They're not variables now, they're like conditions. P is a condition, Q is a condition. This statement here, P implies Q, means that if P happens to be true, the condition P happens to be true, then the condition Q must also be true. And of course, you can rephrase that the other way. If not Q, then not P. If Q is not true, then P could not be true. Because otherwise, by implication, Q would also have to be true. So those are equivalent. Okay, now let me talk about the 2 that actually matter for this class, these last 2. And that is to say P is sufficient for Q. It's the same as what's written here. It means that P implies Q, or if P happens, then Q has to happen. Usually for this class, it will be like Q is the thing you're trying to show. What might you be trying to show in this class? You might be trying to show that the function f of x is maximized on the interval a to b when x equals c. And x is an interior solution. Like, right, this first thing, go back to the top bullet point. Let's say C is an interior solution is really what you're trying to show. You're trying to show that. You're trying to convince anybody who's reading that C is an interior solution. You might want to find something that I would call, but something like a P, where P is a condition. And if you can say P is sufficient for Q, And I can prove that P is true. I can prove that P is a true statement. And if P is sufficient for Q, that means I also know Q is a true statement. So here's how you will use this. Find some conditions that you can show, call them, you don't have to call them P, but they represent P, such that they're sufficient for the thing you do want to show, which is C is a solution. And I will talk about these conditions later. They have names. The first is called the first order condition for maximization. And then the next is called the second order condition. Not very complicated names. They're pretty simple names. But the reason they're called first order and second order isn't because of like the number of derivatives that you're taking or anything like that. It means the first order is the condition you have to show is true first. You can't do anything until you've shown that. Once you've satisfied that, then you look at the second order condition. So I apologize if this is a long-winded way to get to really just the terminology. I would love for everyone to just be comfortable with talking about what is a sufficient condition for maximization? What is a necessary condition for maximization? And what's the difference between those two? So hopefully you guys I haven't talked about necessary very much, but you guys have any questions about sufficient? When I say find a sufficient condition for maximization, what I'm saying is show that this stuff is true, the P stuff is true, that implies the maximization is true. That's what I mean by sufficient, okay? You have any questions about that? Hope I haven't lost you. Doing math is actually more fun than talking about the logic behind the math. Doing something that's even less fun than math. I'm sorry about that. How do I make this fun? I don't know. Make it into some kind of game. No, what time is it? I've lost all ways to check the time. I'm just going to leave this. Okay, it's 1:34. We have what, 11 minutes. Okay. Let me talk about what it means to be sufficient. I'm sorry, necessary. For something to be necessary, it's the opposite direction. This here is equivalent to saying Q is necessary for P. So if I ask you to find a necessary condition, or you yourself are finding a necessary condition for something that you care about, something like optimization, it doesn't mean that you've definitely found the maximum. What does it mean? Why would you ever care about a necessary condition for maximization? Isn't the whole goal to prove that it's a maximum? Yes. And to do that, you need a sufficient condition. I just want everyone to, I can't tell if you guys are getting this, that I can't see your faces. I see Jordan's face. Jordan is the only face I see. I'm going by Jordan. You represent the entire class right now. Your level of understanding of this logical, I'm really just talking about the terminology here. Your understanding of the logical terminology is determining the entire class's, at least my estimate of the entire class's understanding. I think the sufficient makes sense, right? It's like, I want to show Q, so all I need is a P that is sufficient for it, and then I'm done. Done it. The other way is a little bit more complicated. It's almost a way to eliminate things that aren't the solution. Okay, so a necessary condition is like saying, well, I'm not sure if I've found the optimum, but if this is going to be the optimum, then the necessary condition must be true. Okay, if the necessary condition is not met, then for sure this is not the optimum. Because so Q is necessary for P. If now if you think of P as the thing, sorry, it's a little backwards here. P is the thing I'm trying to prove, and P implies Q. If I find that Q is not true, then for sure P is not true. Okay, so that's what a necessary condition does. It says, well, I'm not sure if I found the answer, but I do know that if this is the answer, if this is going to be the answer, then at least the necessary condition should be true for optimization. So I haven't even told you what the conditions for optimization are yet, but there will be two types of second order conditions. One is sufficient and one is necessary, and you use them differently. The necessary condition is used to eliminate things that can't be the optimum, whereas the sufficient condition is used to prove the thing is the optimum. And this is, of course, all ideally. Ideally, this is what you would like to do. It could be that this is not really even possible to do, but if you can, that would be nice. I think I should go on because we're running out of time, and this is enough to talk about logic for one day. Here's the first order condition. I want to give these to you. And I think I'll post some homeworks later so you can start working on it too. This is a necessary first order condition, what I'm showing you right now. Given the problem, maximize x in the interval a to b of f, the function f of x, f is differentiable. If x equals c is an interior solution, then it's necessary that f prime of c equals 0. What does that mean? It means that f prime of c is not equal to 0. It's definitely not a maximum or a solution. If it is true, then maybe it is. I'm not sure that it's the solution, but it might be. So think of this first order condition as something which is necessary to find an interior solution. If you're thinking ahead right now, you might be like, well, just because you're saying it's an interior solution, that might be true, but that's clearly not true for corner solutions. And you're right. Something could be a corner solution, and it might not satisfy this necessary first order condition for optimization. So let's just do it separately. Let's do it separately. First, let's look for the interior solutions. Let's see what those could be. Then look for the corner solutions. See what those could be. Either way, by doing both of these, you will have checked for all possible solutions. Okay, and it's called the first order conditions. I'll often just write FOC for that, FOC. Here's another interesting thing. It's the same whether you're talking about max or min. I wrote max here. If I wrote min, max, it's the same condition. What you're looking for is the derivative of the objective function and setting that equal to 0. So that's the first thing you do in one of these problems. Take the derivative of the objective function and set it equal to 0. You will find all the stationary points, and those are the only things that might be the solution, at least in the interior. You guys have any questions about that? It's called the first order condition, and it's a form of a necessary condition. It's not sufficient, but it's necessary. Running out of time. A couple more minutes. Now let's talk about the second order conditions. We've made it this far. Let's go all the way to the second order conditions. Blowing up over here. Okay. So let's talk about the second order condition for maximization right now. If I have a problem, remember it looks like this. You can read it right here. Objective functions here, choice variables here, choice set is here. F is differentiable and the FOC have been met. Remember, that's what it means to be first order. The first order condition, let's say they've been met for something called x equals c. Once we've got that, once we've got the first order condition, then you look at the second order condition. And that is to take the second derivative of f double prime of c. And if it's negative, that's actually sufficient. It's no longer necessary, but that's sufficient to show that C is not a global max. Sorry, we still don't know if it's a global max, but we know it's a local maximum. Okay? So F double prime of C being negative is a sufficient second order condition to show that C is a local maximum. I have to say all of those words for it to be correct. If I abbreviate it, it becomes imprecise and actually incorrect. So I want you guys to know the first order condition and the second order condition for maximization and minimization. Good news is, let's go back to first order condition. That's the same whether you're doing a max or a min. But the second order condition does change. It's F double prime negative for a max, and it's F double prime positive for a min. I already said that when I was talking about the bowl and the hill. The top of a hill is a max. The bottom of a bowl is a min. So that's kind of obvious, I think. By the way, I've also given you on this slide what the necessary second order conditions for maximization are. And they're actually very, very similar. The difference is F double prime C, it could be less than or equal to 0. So if you take away the or equal to, it becomes a sufficient condition. If you add the or equal to 0, it becomes a necessary condition for maximization. And similarly for min, if you add the or equal to, it becomes necessary instead of sufficient. And I just went through all of that talking about what's the difference between necessary and sufficient to try to, it's about language right now. It's about just making you comfortable with what the language, what those terms even mean when I say, oh, what's the necessary second order condition for maximization? I'm saying what at least has to be true for it to possibly be a maximum. If I say what's the sufficient second order condition for maximization, I'm saying what is a way to prove that this is actually a maximum? Okay, we are running out of time. So I think next class we will actually do some of these problems. I haven't done any of these problems yet. Apologize for that, but it takes a while. I feel like I'm going slowly, and as part of the virtual learning environment it makes it difficult to tell just exactly how fast I